Hello everyone, this is Professor Roman. Welcome to the 31st video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we'll continue our discussion of recurrence relations. We're in section 6.2 now of the accompanying book. Second order linear homogeneous recurrence relations with constant coefficients. And I'll break all that down in a minute. Unfortunately, there's no general method for solving all types of recurrence relations. But there are some important classes of recurrence relations for which methods are known. And the class we're going to discuss right now is the one from second order linear homogeneous recurrence relations with constant coefficients. That includes the Fibonacci recurrence relation that we looked at earlier. So here's the formal definition. A second order linear homogeneous recurrence relation with constant coefficients is a recurrence relation of this form. Sn equals a Sn minus 1 plus b Sn minus 2. For n bigger than or equal to 2, where a and b are constants and b is non-zero. Okay. We could actually start this at other values of n. This would start it at s naught, s sub 0. But that'll do for our purposes. We could start this at n equals 3 or any value of n, really. The term second order refers to the fact that this member of the sequence is present, Sn minus 2. The Sn minus 1 sequence may be missing because a could be 0. The recurrence is linear because it doesn't involve any powers of the terms in the sequence, other than the first power, of course, or products of members. They could, if this was Sn minus 1 times Sn minus 2, that wouldn't be linear. So, for example, this is, so that's what I just said here. This one's a non-linear recurrence relation. This is also non-linear because it has Sn minus 1 squared. The recurrence relation is homogeneous because it does not have a non-zero constant term. So this is a non-homogeneous linear recurrence relation. This recurrence relation does not have constant coefficients because n is not constant here. So putting it together, second order, because of the Sn minus 2, b is non-zero, linear because this is a linear combination of Sn minus 1 and Sn minus 2. No powers higher than 1, and no products. Okay. Homogeneous because there's no constant term, constant coefficients because a and b are constants. The first thing that we should notice is that a recurrence relation of this form, together with the two initial conditions, S naught equals U, S1 equals V, so U and V are known, completely determine the sequence Sn. So in other words, there's exactly one solution to this equation, this recurrence relation, for each pair of initial conditions. The second thing to notice is that if we have two solutions, Rn and Tn, to the recurrence, then any linear combination, CRn plus DTn, or C and D are constants, they don't depend on n, is a solution. And that's just a matter of plugging things in. So I'll let you look at that. Now, the remarkable thing about second-order linear homogeneous recurrence relations is that they have a particularly simple solution. I should add, with constant coefficients. Sn equals r to the n. R is a non-zero constant. Plug that into the recurrence relation, and you get this. Canceling r to the n minus 2 gives us a nice little quadratic equation in R. So if R is any solution to this quadratic equation, then we can reason backwards. Then this holds, so this holds, so this holds. And r to the n is a solution to the recurrence. All we need to do then is worry about dealing with the initial conditions. The solution Sn equals r to the n has initial conditions S naught, n equals 0, is equal to 1, and S1 is equal to R, so they may not, that solution may not fit the situation at hand if you have different initial conditions. But it's easy to tweak that, as you'll see now. This is a really important equation. It tells us almost everything about this type of recurrence relation. It is called the characteristic equation for the recurrence relation, and its solutions are called the characteristic roots of the recurrence relation, and these are terms you may have heard before if you've studied linear algebra in a different context with regard to eigenvalues. So here is the whole summary of these types of recurrence relations, their solution. Consider the second order linear homogeneous recurrence relation, again with constant coefficients and with initial conditions S naught equals U and S1 equals V. And this is the characteristic equation. If the characteristic equation has two distinct roots, R1 and R2, then the general solution to the recurrence relation is given by C1 R1 to the n plus C2 R2 to the n. That's Sn. And C1 and C2 are constants which can be chosen any way you want. So we choose them to satisfy the two initial conditions. We have two requirements. We need two parameters, C1 and C2, in order to make these conditions to be satisfied. If the characteristic equation has only one, so it would be a double root, R, then the general solution is C1 plus C2n times r to the n. And again, C1 and C2 would be chosen to fit the initial conditions. Well, part one we've really already done. R1 is a solution to the characteristic equation. It's a characteristic root. Therefore, R1 to the n is a solution. C1 times R1 to the n is also a solution. Same thing for this term. And the sum of two solutions is a solution. So part one is taken care of. For part two, the fact that the characteristic equation has only one root tells us something about its form. It has to be the quantity x minus r squared. It's monic, so there's no, the coefficient of x squared is 1. So this is what the characteristic equation looks like. So a is 2r, b is negative r squared. Substituting this into the coefficients, for the coefficient, the original recurrence gives us this recurrence relation. So that's the form of the recurrence relation when the characteristic equation has a double root r. And then all we have to do again is plug in to see that this is indeed a solution to the recurrence relation. Okay. So 2r Sn minus 1, this is Sn minus 1, minus r squared Sn minus 2, and then the simple algebra, and we get Sn. Okay, let's look at some examples. For the recurrence relation, Sn equals 2Sn minus 1 plus 3Sn minus 2, and these two initial conditions, this is the characteristic equation, and the roots are negative 1 and 3. So this is the general solution to the recurrence relation. And in order to determine the two constants, we need to use the initial conditions. So when n equals 0, we have S naught equals 0, so 0 equals S naught equals C1 plus C2. Similarly, for S1, we get this equation. So we have two equations and two unknowns. Solving them gives us C1 equals negative 2, C2 equals 2, and here is the solution. Okay. The hard work's been done for us. Solving these problems is just high school algebra, solving the characteristic equation. So this one's going to be similar. This recurrence relation with these initial conditions. This is the characteristic equation. It has only a single root, x equals 2. So this is the form of the general solution. Here, the x is 2, so that's why this is a 2 here. And the initial conditions, again, give two equations in two unknowns. So here we have the general solution. It's always wise to stick this into the original recurrence, make sure you didn't make any algebraic mistakes. Something that I am prone to do, by the way. Anyway, let's consider now the Fibonacci recurrence relation. That's this one, with these initial conditions. This is the characteristic equation. Solutions are these two. It's beginning to look a little nasty. So the solution to the Fibonacci recurrence relation, this is the general solution to the recurrence. This, the initial conditions, S naught and S1 are both 1, gives us this equation and this equation. Solving these, we get C1 and C2. So this is the solution to the Fibonacci recurrence relation. Okay. And this is important, so I put it in a theorem. In all its glory, this is what the solution looks like. Okay. Now there's two points here to be made. One minor, I guess you'd say, the other major. What's remarkable about this is that Sn is an integer, which means no matter what you put here for n, this mess has to be an integer. Okay. So that's a surprise. But the real important point is this. As I mentioned before, there's no general method for solving all recurrence relations. But that's not necessarily as bad as it may sound, because there are many instances, and this is one such, where the recurrence relation itself can be much more useful than its solution. If you needed to compute, for example, the first 10,000 Fibonacci numbers, how would you do that? Well, you'd use a computer. But you don't want to feed the computer this formula, because as soon as it sees the square root of 5, it's going to start to smoke. It cannot represent that number exactly in computer memory. So you immediately will introduce rounding errors or precision errors, and the values you'll get for Sn will be unreliable. If, on the other hand, you feed the computer the recurrence relation and ask it to do 10,000 iterations, that's not a problem at all. You'll get the exact answers, assuming, again, that there's no overflow or rounding errors. But you're much more likely to get the exact answer that way than you would with this formula. So in short, the recurrence relation is, at least from a computational point of view, a lot more useful than the solution. Okay, that completes this section. What's coming next will be second-order linear non-homogeneous recurrence relations with constant coefficients. Here's the definition. A second-order linear recurrence relation with constant coefficients is a recurrence relation of this form. This part would be the homogeneous version, and if f of n is non-zero, we have a non-homogeneous recurrence. So this is a and b are constants, and f of n is a function of n alone. It's not a function of any members of the sequence. If f of n is non-zero for any single value of n, then we have a non-homogeneous recurrence relation. But in this definition, I haven't restricted f of n in any way, so this general form here would refer to any second-order linear recurrence relation with constant coefficients. If we drop the Fn term and just look at this recurrence relation, it is referred to as the associated homogeneous recurrence relation, associated to the original recurrence. And there's an interplay between these two that we're going to discuss in a minute. So here's an example of a non-homogeneous recurrence relation of this type, because f of n is 2n. In this case, f of n is 4. It's independent of n, so both of these are non-homogeneous recurrence relations. Well, in general, there is no known method for solving non-homogeneous recurrence relations of this type. For homogeneous recurrence relations, as we saw in the last video, it's quite straightforward. Compute the characteristic equation, find the characteristic roots. Unfortunately, that doesn't work for non-homogeneous recurrence relations. Nevertheless, there is much we can say. First, if Pn is a particular solution to the non-homogeneous recurrence, this one here, we'll assume this is non-homogeneous, and if H sub n is a solution to the associated homogeneous recurrence, then the sum is also a solution to the non-homogeneous recurrence. And I'm going to leave that for you to prove. We did something similar in the last video. Second, if Rn is another solution to the non-homogeneous recurrence, so we have Pn and Rn, both solutions, the difference is a solution to the homogeneous, the associated homogeneous recurrence. And again, I'll let you verify that. Therefore, we know that all of the solutions to the original recurrence, the non-homogeneous one, are precisely sequences of this form, where Pn is any one particular solution to the recurrence, and Hn is any solution to the associated homogeneous recurrence. In other words, all we have to do is find one solution, and we can get all the solutions just by tacking on the solutions to the associated homogeneous recurrence, which we know how to find using the characteristic equation. So here is a summary. Well, that's progress, but still we don't have a method for solving, even finding one solution to the non-homogeneous case. But we can actually guess at the form of a solution, and if we're lucky, we verify it by induction. The reason that this works, we don't have to just guess out of the blue, is that frequently one of the solutions to the recurrence has the same form as this term, f of n. And let's look at some examples. You'll see what happens. So here is a non-homogeneous recurrence. I'm not going to keep saying second order, linear, constant coefficients. That's all we're dealing with now. So here's a non-homogeneous recurrence. This is the associated homogeneous recurrence. Its solutions are given by this, and I'll let you check that. The constancy is determined by the initial conditions. To find a particular solution to the original non-homogeneous recurrence, we try a solution of the same form as f of n, which in this case is n minus 4. So what is n minus 4? It's a linear polynomial in n. So we try this, where a and b are as yet to be determined. Substituting this into the original recurrence looks like this. Equating coefficients of n and the constant terms gives us a system of equations, linear equations, which we can solve for a and b, and we have found a particular solution. And I would strongly urge you to double check by plugging that in. It's easy to make a mistake here. So the previous theorem tells us then that all solutions to the recurrence, where is it? Right here, have this form. an arbitrary solution to the associated homogeneous recurrence, that's why there's still a constant here, plus this particular solution. And now we can use the initial conditions to determine the constant C. So if the initial condition is S naught equals -1/9, then that means that all of this, when we put in n equals 0, has to be -1/9, and C has to be 1, and so we get the actual solution to the recurrence with this initial condition. Okay. Another example, non-homogeneous recurrence. The associated homogeneous recurrence has this solution. To find a particular solution to the non-homogeneous version, we try, a quadratic in n. So that looks like this, general quadratic. We have to determine A, B, and C, and so we substitute into the non-homogeneous recurrence. We get all of this stuff, equating coefficients of n squared and of n and the constant terms, 3 equations in 3 unknowns. Here's the solution. Here is the particular solution to the recurrence. The general solution looks like this. Finally, here is another non-homogeneous recurrence relation. F of n is 3 times 2 to the nth power. So the associated homogeneous recurrence, characteristic equation, get the solutions. Here's the general solution to the homogeneous recurrence. And we will try something of this form, a times 2 to the n. Substitute into the original recurrence, divide both sides by 2 to the n minus 2. We'll get this equation, a equals -3. So this is the general solution. There's plenty of problems for you to practice on. And then we're going to move on to the last section in the chapter on recurrence relations, and that is the use of generating functions to find solutions to recurrence relations. So it's a short video, but I would urge you, if you want to kind of hang on to all this, to work some of these exercises. Solutions are at the back of the book. Thank you for watching, and I hope to see you in the next video.